start the recording. So everybody should be aware that as a participant in the workshop, all the workshop sessions are being recorded. The recording has now started. We're also following the NDSS Code of Conduct, which can be found on the NDS website or by this link in the slide chairs, the chair slides, and these slides are available on the agenda page. So what we're going to ask folks to do is mute themselves during the presentations rather than enforcing a mute across the whole meeting. We're going to ask folks to mute themselves when speakers are talking. At the end of each talk, we will have a 5-minute Q&A session, and each session also has some additional time at the very end if you want to hold on to your question to the end of the session. The way we're going to work it today is that we're going to use the Zoom chat window as a question queue. So the idea would be that you either use a plus or minus queue to enter or leave the queue for questions. And we're going to reserve the Zoom chat just for that. And we'd ask that all ongoing discussion about a talk is done in the Slack channel so that we can separate those two streams of information. Some other logistics for today. The Zoom chat will be for questions only. The workspace we'll use for discussion. We do have note takers for each of the sessions, and we will publish those notes after the workshop. The NDSS has also set up a GatherTown space that can be used during the break and social sessions. So we're sort of asking, I think the idea is that if folks concentrate on the presentations during the sessions, and then we can use that for socializing outside of the session times. And I think there's more details about that on everybody's dashboard. And we will also be tweeting throughout the day, so please feel free to join us. Our hashtags are DNS Privacy 21 and NDSS 21. So without further ado, we will start with session 1, measurement of encrypted DNS. And the first talk is Oblivious DNS over HTTPS, that's ODO, a practical privacy enhancement to DNS presented by Sutij Singhanamala from the University of Washington. So please go ahead and share your screen and start your talk.
Hello. Thank you so much. Hi, everyone. Good morning from rainy Seattle today, and thank you all for being here. I'm Sudhish. I'm a PhD student at the University of Washington, and I'll be presenting the feasibility of a new privacy-enhancing DNS protocol called ODO, or Oblivious DNS over HTTPS. And this work is the result of a collaborative effort between lots of incredible people at Cloudflare and during my summer with them as an intern. And I'm delighted to be representing all of them in today's talk. So as a quick introduction, DNS is the domain name system and is the foundation for the human usable internet. And it responds to client queries for host names with the corresponding IP addresses and records. And traditionally, the DNS protocol is not encrypted, and it uses UDP, which continues to be a majority of the traffic that is received by the public recursive resolver that Cloudflare operates. And the usage of non-encrypted DNS kind of leaks user information to network operators, to on-path adversaries who are observing the network, and even allows active attackers to modify the request from the client or the response from the resolver. To overcome some of these limitations, there have been a lot of recent efforts to secure DNS using DNS over TLS or DOT and DNS over HTTPS or DOH. And both of these have been gaining popularity and have been integrated into various web browsers, operating systems. And these protocols ostensibly protect client traffic from being observed by onlookers or being intercepted and changed by attackers. But however, there is still a problem. the resolver operator can continue to associate the client requests to their IP address and build a profile around their browsing patterns if they would like to. So over the last few years, we've seen some active measurement research trying to understand and measure the impacts of encrypted protocols like DOH or DOT. And many large-scale measurements have shown that the performance of encrypted protocols actually vary by the choice of the resolver. And it does not significantly impact the page load time, and it improves user security. So there have been various attempts to improve page load times by also doing DNS prefetching. But while DOH did actually improve the security of DNS queries for the clients, it also received a lot of criticism because of the small number of publicly available resolver services, essentially centralizing the internet and giving these organizations a lot of control. So these resolver operators can associate the client queries with the client's IP addresses and use the IP addresses to geolocate their clients. To maintain some privacy guarantees, some operators like Cloudflare actively purge data exceeding 24 hours and give their users a privacy policy-based guarantee. But bringing together organizations to agree on a common set of privacy practices to maintain the user privacy, it requires a lot of explicit negotiation and effort. And Mozilla, for example, has done an incredible job and actively defined the criteria around data retention, around aggregation, and frequent audits for a DOH service to be configured as their default in the Firefox browser. But for some users might really be like comfortable with the idea of a policy-driven approach, but these are difficult to enforce, and they're also time-consuming, making users want a system that can technologically guarantee their privacy. And in this talk, I'll kind of focus on how we address some of these privacy critiques and prevent the ability for resolvers to be able to create a profile of their clients. And this is exactly where oblivious DNS over HTTPS or ODOH kicks in. And at a high level, there are three main components in ODOH. The first are the clients who prepare the query for which they would like a response. And the goal of the clients in ODOH is to be able to kind of successfully send encrypted messages, receive a valid response, and decrypt them if they're the intended recipient. And in the process, also be able to identify if there was any malicious actor on the network path and take any corrective actions, which could mean changing the DNS resolver that they're using or changing the proxy. So the second is really the proxy. And the main role of the proxy is to kind of relay the encrypted queries to and from the third one, which is the target or the resolver. And the goal is to remove the IP addresses of the clients from being sent further towards the resolver. And the third is a target instance, which kind of receives the encrypted queries that the client needs a response for, decrypts it, obtains the corresponding DNS response for the query or the DNS answer, and then prepares an encrypted response to send it back to the client through the proxy. And in the process, it has no ability to identify who the actual client was by their IP address. So it effectively decouples the IP addresses of the clients and the responses or the queries that they have made. So at a high level, the design of ODOH is similar to that of DOH, but it kind of injects this intermediate proxy node, which terminates a client query. And it performs the query on the client's behalf. So for a website x.com for which you would like an answer, the client prepares an encrypted query queue and forwards it to the proxy. The proxy terminates this connection and then sends this encrypted query queue to the target who then decrypts the connection. And the guarantees for privacy, however, this make it different from a proxy DOH, where the client's DOH query in the previous case probably could have been seen by the proxy. And the main goal over here is to prevent the recursive resolver and the ISPs running such recursive resolvers from being able to link the clients to their request. And the security model here is, it kind of builds on this premise that the proxy and the targets do not actually collude. And this is a critical part of the design. So clients need to choose proxies and targets such that they are not operated by the same entity or known to be colluding. But additionally, we also assume extended Doleviev adversaries who have this ability to create, drop, and modify messages. And we also give them this ability to compromise TLS sessions in our analysis for the security of the protocol. And practically, colluding adversaries on various network links who can decrypt the connection and read the message contents can create some kind of an association between the encrypted query and the encrypted response. And the compromise of the resolvers like secret key, for example, could help such and aid such attacks. So a client kind of in the overall ODO scheme encrypts the DNS query using a hybrid public key encryption scheme and uses a validated public key of the target resolver. And then sends this query to a proxy instance that can be democratically like spun up by anybody to use. So there are various ways in which the bootstrap of or the knowledge of the original keys can be obtained, and they can be validated through DNSSEC validations, look for any conflicting keys. But for now, I'll kind of punt on that problem. So in ODO, the proxy instance can see the IP address of the client, but not the contents of the DNS query. And it forwards this message to the oblivious target, which decrypts the query and obtains the response from the resolver. And the response is encrypted by the oblivious target and sent back to the client where this message is decrypted and successfully the answer has been received. So in this process, the target only sees the DNS contents and not the actual client's IP addresses. But we often say that the target and the resolver to be independent entities in this architecture that you see here, but this need not really be the case. Ideally, in practice, for performance reasons, the oblivious target and the recursive resolver could be co-located to avoid additional network messages that are being sent between the target and the resolver. But however, it is kind of still possible to maintain these as individual services without co-location, but that has some impacts to performance and page load times. So with the understanding of the protocol in place, we set out to understand and measure three main research questions. The first one being, what is the impact of ODO on the DNS response times? And how does ODO actually affect page load times and user experiences? And how does ODO compare itself to other privacy enhancing protocol variants that are out there today? And this kind of helped us understand the cost of privacy for the user and while maintaining the security guarantees that the encrypted DNS protocols provide. So this slide pretty much sums up the results of our measurement study and is probably of the most interest in case you want to revisit. So I'll leave this here as a reference. But over the next few slides, I'll kind of talk about the measurement that we've done and go through each one of these results in itself. So let's get to the measurement. And we implemented and deployed the oblivious targets and proxies using Google Cloud and a serverless platform like Cloudflare Workers. And we physically separated the oblivious target instances from the resolver like we saw in the architecture. And we randomized the queries from the target to three public resolvers, to Cloudflare DNS, to Google DNS, and Quad9, which we used in our measurements. And the services are hosted in 9 Google Cloud data center locations, so 7 across the United States, 1 in Montreal in Canada, and 1 in Sao Paulo in Brazil, with 10 client instances that are running at each one of these vantage points, performing an experiment where they're sending DNS requests at a rate of like 15 requests per minute, with the average number of DNS queries being sent, which is kind of like the average number of DNS queries that are being sent by clients who have heavy internet usage. And the average bandwidth for all the clients running in the experiment is roughly 480 megabits per second, but we've also kind of performed traffic shaping experiments with to see the impact of ODO in 2G, 3G, 4G, and 5G settings. So the clients performing the DNS response time measurements actually choose a proxy and a target pair. And there are various possibilities among the available proxies and targets. But what we noticed is that by choosing a low latency proxy target pair for the measurement, which is shown by the orange line here, we find that the average query response time actually improves by 22.8% compared to only choosing a low latency proxy, which is shown on the green line. And this kind of hints towards the fact that having an intermediate proxy on the same network path will improve response time performance. But this path can, however, be quite different from the traditional path of a DNS packet, of a UDP-based DNS packet. But what about connection reuse? HTTPS gives us this ability to do connection reuse, and connection reuse is an optimization that can help the clients improve their performance by at least 48% on an average. And it basically does this because it avoids unnecessary TCP and TLS handshakes for every request. But however, the reuse of connection could leak some information because the session key is shared, but it does not leak any sensitive information as such because either in clear text or because everything is end-to-end encrypted between the client and the target at this point. So in our experimental setup so far, we kind of evaluate for this worst case performance, and we incurred an additional latency between the target and the resolvers among the choices of resolvers that we have. And as we see here, the target instances which are located in Google Cloud, which is the green line, kind of tends to have much faster response times. And this is probably because the Google DNS services are co-located inside the same data center when we're using Google Cloud. And this kind of hints towards the fact that there potentially co-location could improve performance. So if we integrate the oblivious target into the recursive resolver, we can reduce the additional network latency, additional network hop of messages that are being sent. And these essentially now become a cache hit for the answer or a cache miss, which incurs the additional network cost for a recursive resolver to kind of receive the response. So using this result, we've kind of engineered that into the public resolver that is operated by Cloudflare for everyone. And so we have a co-located version of oblivious DNS over HTTPS, where the target and the resolver are now one single entity.
These just a time check. You have 5 minutes until QA.
Okay. Yeah. So sorry. So to understand the performance of ODO, we kind of compare this to other protocols offering similar privacy and security guarantees. And we use DO as the baseline, which is shown here on the blue line to the left, and DO over TOR, which is shown as this orange line on the right. And when compared to ODO in green, we notice that ODO with like no service co-location achieves this interesting position roughly between DO and DO over TOR. And the results get interesting and better as we start to co-locate. And this is the performance of the ODO resolver that Cloudflare operates, which is the purple line. And we notice that the response times compared to DO as the baseline increase on an average by 50% with service co-location and 100% when the target and the resolver are actually not co-located. So, but DNS protocols with message encryption like DNSCrypt tend to have larger compute overheads and use non-encrypted channels. And these protocols also have a higher response time and lie somewhere between ODO and DO over TOR, which is shown over here through the dotted line. So here's a slide for reference, which you could revisit to see the comparisons of various DNS protocols and also the impact of network architectural variants. And where ODO fits in along with the protocol security and privacy guarantees. So this brings us to kind of a crucial measurement that we're interested in, and that's the page load time impact. And to do this, we run a measurement node in a lab network connected to a commercial ISP. And the node runs a local stub resolver, which is configured to use DOH or ODOH for various runs. And the same set of web pages, after purging any local caches, are run again. And the measurements presented here use the public ODOH service that is operated by Cloudflare. So it's the co-located setting. And we find that using ODOH with the proxy kind of increases the page load time by 13% compared to baseline UDP-based DNS. And the non-co-located variant kind of increases it by 20%. So the average page load time for content changes from 1.8 seconds with DOH 53 or UDP to 2 seconds with ODOH. And the results so far kind of look optimistic, but it is still ongoing work. So to conclude, I mean, ODOH is a practical privacy-enhancing protocol for DNS with minimal page load time impacts, and the performance impacts of the protocol are kind of purely network topology effects. So we make some recommendations for ideal usage in production systems and how having an ecosystem of on-path proxies and service co-location and connection reuse at the stub resolver can kind of help. So the code and the implementation is open source and is available at the Cloudflare GitHub organization page. And we're kind of committed to moving this standard forward in the IETF and hope that more operators join us in support for the protocol. But just as I end, I would like to give a huge shout out to all the authors of the draft, Tommy and Eric and Chris, in addition to the incredible team members at Cloudflare, without whose effort this would not have been possible. And thank you. I'm open to questions.
Thank you very much for that very interesting presentation. We have a couple of questions. First one is from Paul Hoffman. Please go ahead and ask your question.
Hi, thank you. And Sadish, thank you very much for the measurements part of the presentation. But so when this was first presented in the IETF, well over a year ago, pre-COVID, many people asked the authors, who are the users of this? I mean, given that this is a larger and more fragile protocol than either plain old DNS or even DOH or DOT, who are the users? And I sort of had hoped that you might explain that more. That is, who would not trust their immediate upstream with their address information, but would trust them not to collude with the resolver itself? That seems to me, at least, like a very narrow market. Can you discuss that more, or maybe hand that off to Chris Wood, who, hopefully would be one of the kind of people who could answer this?
Yeah, I'd like it if Chris can also chime in, but so from my understanding of this, it feels like there definitely is probably a market for this, especially given the number of users who have been taking up DOH as a replacement. But the concerns are valid that organizations like Cloudflare or Quad9, for example, could, if they wanted to, profile and build this profile of users. And there is like an audit-based mechanism which kind of stops that. So I feel like technologically guaranteeing it might be a good way to do this. But additionally, one of the factors here, which I kind of did say in the presentation, was how the user chooses two independent entities, and how does the user really know if these entities are colluding, right? I think some ways to do that is to kind of continue having these like Mozilla trusted recursive resolver style of like pages, where there is some organization that the user trusts who can vet the proxies and kind of tell what kind of proxies these are. Are these logging proxies, non-logging proxies, for example, and what's the behavior at the resolvers, and so that the user can kind of take a better decision. But I think a lot of this has to deal with also how we bake the feature into browsers or into operating systems. And for DOH services, I think the configuration is kind of simple, where they enter the IP address or like 1111 or 8888, and if there is a DOH service that is allowed, it kind of picks up and works on that. But having two text entry fields, one for the resolver and one for the proxy, can make it kind of challenging. So I feel like there are some user experience like research that probably needs to go into this work. And maybe Chris has some more answers to that.
Can you hear me okay?
Yep.
Yeah, I think you summarized it nicely. Effectively in our conversations with various clients, anyone who's primarily interested in adopting DOH to sort of remove certain adversaries along the path from seeing what they're querying and what they're trying to do online. Also consider effectively the resolver to be malicious. And the reason why DOH was rolled out the way it was is because we didn't have something like Oblivious DNS, a scalable version of Oblivious DNS at scale that could be adopted out of the gate. So I think that this is just sort of trying to fill that gap. So clients that are trying to move towards DOH, towards encrypting their DNS, have expressed an interest in this particular protocol, whether or not it's scalable, performant, et cetera, and whether or not we can work through sort of the configuration issues that Sadish mentioned are certainly good questions and open questions at this point. But that's primarily the target audience from a client-facing perspective. Now, from a consumer or from a resolver-facing perspective, some of the interest is also around trying to break up centralization and make it so that clients can perhaps distribute their queries to more resolvers without a fear of consolidating the internet. So there are multiple facets here multiple angles here that we're trying to lean on to get this protocol out and adopted. But there's still lots of open questions in terms of how we actually do that. Thanks for the question, Paul.
Yeah, thank you, Paul. I'm going to jump. We have quite a queue of questions, so I'm going to take a few more, and any I don't get to, we will re-queue you in the session at the end of this session, so everybody will get a chance to ask them. I'm going to jump now to Philip Winter, who's next in the queue. Philip, if you could ask your question, please.
It was already answered, but thank you very much.
Oh, okay, awesome. Thank you. Okay, that means Sandra is next in the queue, please.
Yeah, my question was answered as well. Thanks.
Ah, wow, you nailed half the queue with that response then. Thank you, guys. So the next one is from DKG. I'll read that out unless you want to do that yourself, DKG. But the question is, how do you handle the metadata leakage due to co-located ODO? Network operator sees statistics and traffic analysis. If they're also the resolver operator, what keeps them oblivious?
So I think there are two things to kind of decouple here. If there was a rogue resolver operator who wanted to see and associate your query, or like I actually identify what the client was doing, they could send a unique IP address and see which client actually connects to that IP address. But that's kind of like out of scope of the security and privacy guarantees that you want to provide for the ODOH protocol by itself. But yes, that is definitely an interesting question and possibly something to kind of target next.
Thank you. Puneet is next in the queue. Please go ahead and unmute and ask your question. Puneet. Okay, Puneet, you should be unmuted now. Okay, I think we lost him. Chris was next in the queue. Do you still have a question, Chris?
Sorry, no, I was just going to respond to Paul.
Okay, okay, cool. We'll take one final brief question then. Pallavi Arismatai has written, would it be better for the client to use multiple proxies in a round-robin sort of manner? Otherwise, the target can start associating queries from a certain proxy. What are your thoughts on this?
Yeah, I think that's definitely like a possibility. So if I can just quickly go back to the performance slide, the random choice is essentially the equivalent of round robin, where you have like multiple connections open to different proxies, and you're randomly allocating probably not purely round robin, but you're allocating in some fashion that you're trying to avoid being known for a specific client, being known that a specific client is using a proxy. But I think over here the challenge is more along the lines of this issue would not really occur if there are lots of users using the same proxy, because for user 1, user 2, and user 3, the proxy would feel like the proxy itself would be the IP address that the resolver sees. But if there are very few users operating using a specific proxy, then yes, it is kind of possible to indirectly create some kind of a reference or some kind of association between the proxy and who the users could be.
Okay. Due to time, I think we're going to take the rest of the questions on this topic at the end of the session, and Chris, you'll have a chance to respond then as well. So with that, I'd like to thank Sadish very much for his talk and for all the interesting questions. And we'll now move on to the next talk in the session, which is measuring DOT and DOH blocking using the OONI Probe, a preliminary survey. It's presented by Simon Basso from the Open Observatory of Network Interference. So please go ahead. We've got you.
Hello.
We can see your slides and we can hear you. Thank you.
Perfect. Okay, great. So good day from Italy. I'm Simone. I work at OONI. And so we did these measurements of DOT and DOH. It's a preliminary one. And so let's start. What's OONI? OONI is a platform for measuring internet censorship. We started off as a part of the Tor project. We are now independent, and we are around since 2012. And we have been measuring censorship. So as I said, for a long time, we collected measurements in more than 200 countries, and we documented many cases of internet censorship so far. So OONI is collaborative in the sense that users install this tool called OONI Probe, and this tool could be a mobile app, a desktop app, or a CLI. And they can choose to run measurements involving the blocking of several things, including websites, instant messaging, and circumvention tools. So what happens basically is that a user starts running OONI, and this collects measurements which are sent to our collector. And then this triggers a pipeline, and the data is stored. And at the end, we have an API that gives to users or researchers that access it, direct access to single measurements, and a website called OONI Explorer that shows pretty measurements. What is the motivation for us for measuring DOT, DOH blocking? So, well, as you know, basically the internet is a very different landscape since the beginning, and we have seen increasingly more cases of states that are asserting their power on the section of internet that they control. And there are scholar articles that argue that this way of asserting control is, so to speak, Westphalian. And Westphalian means, so it stems from a peace in Europe in 1648, the Peace of Westphalia, and you see here, like in this slide, a picture of that. And basically means absolute power over a territory. So scholars argue whether this is the right model. This is not what I'm going to do here. I'm just want to describe the way in which basically this happens. So for DNS, if I'm a DNS user and I'm using my ISP resolver, and I'm querying something that I should not, well, because it's illegal in that state, then what could happen is that the authority goes to the ISP and says, look, when someone asks for those queries, then you should either annex domain them or maybe return localhost or whatever, but this should not work. So this is usage of authority within the boundaries. When this service is a public resolver located outside, so like Google Swan, Code9 Swan, etc., then it's of course possible to go abroad and ask for the same, but it's more convenient to go to the ISP again and say, look, if you can intercept or filter the queries in some way, just make sure it does not happen that these queries are successful. And then in this picture, in this situation, let's say we have the emergence of DOT and DOH, and they are, in our experience and on based on what user tells us, very widely used in many countries because they really help to go around this sort of censorship. But this brings with it the research question that we had, which is, are those services working? Are those services blocked? And if so, how? And this leads us to the experiment. So we added to OONI one extra experiment, which is called DNSCheck. And this diagram here shows the logic of the experiment. So let's just start from the top. The top bubble, the blue one, is the input to the experiment. So in this case, we have two parts of the input. We have a URL that says, I want to use DOT and I want to use DNS.google as a resolver. And then the second part is, this is the list of known good IP addresses for this service. Now, the DNSCheck experiment is composed of two steps. The first step is called bootstrap. The objective of bootstrap is like, if the URL contains a domain name and it's not like 1111, but it's a domain, then we use the whatever resolver is system resolver for the user, and we see if that leads us to an IP address or an X domain. Whatever we get from this first step, we add to the set of known IP addresses. And in this example, I'm showing you a clearly bogus response, which is localhost, but it also may be good, or it also may be an X domain. Whatever happens, now we have an augmented input, and then we go into the next step, which is called lookups. What does it do? Well, for every IP address that we discovered, plus every IP address that we knew at the beginning, we are trying to connect to this IP address. We do a TLS and check with it, and then if everything is successful, we issue a query, and then we record the reply. So this is the best case in which everything works, but of course connect may fail and the TLS and shake may fail, or there may be something wrong while we issue a query and receive the reply. And in this slide here, I'm showing three cases. So the first one for 88888 is like the successful one. Then on the second line for 8844, we see, for example, an handshake timeout, and in the third one, a connection refused. So this is the logic and the tool that we used. Then let's discuss the measurements campaign. So it spanned for a little bit less than a month. We considered as input 123 DOH services, and we actually looked to the Wikipedia page about that, and we compiled the list out of that. Then, given this list, we expanded this list by resolving every domain that was in the list, and this leads us to 461 either TCP or quick endpoints. Now, the paper itself and this presentation, they are only on DOH over TCP. We also did run some DOH over quick, but since the code was being written basically at the same time, we considered it better to leave it off this initial investigation. Another thing to note is that the measurements that I'm discussing, they are not from the official OONI client, but from an experimental client that's called MiniUni. And we have a bunch of users that they are more into testing experimental stuff. So this client allows them to test new stuff and help us refine it. And out of all the measurements that we run, I'm going to tell you here about just 3 ASNs in 3 countries, which are Kazakhstan, in which the tests were run from a VPS, Iran, where they originated from a mobile network, and China, again, from a VPS. Now, what are our main findings? So if you recall, I told you that there are 2 steps, bootstrap and lookups. And bootstrap was actually, well, in most cases successful, and we didn't see many, well, actually, we didn't see any NX domains, but we did see just one case, dns.adguard.com, which was resolving to a well-known bug on IP address in Iran. Apart from that, bootstrap was good, and all the rest was just well, the rest of this presentation just discusses the lookups that we performed. So the first thing to note is that apart a few cases, most endpoints, they were either always failing or always succeeding. For 1111 and 1001, it was a bit weird, the behavior, since every few days it flipped from blocked and non-blocked in the Kazakhstan ISP in which we ran tests. And the same we observed in Iran for 1111. We don't have a very good explanation for that. And then another thing that we noticed was that the Japanese blood DNS DOT endpoint, it was initially blocked when we started measuring, but sometime around the night of the 1st January, it stopped being blocked, and then all the queries after that were successful. So now another thing to note, if you look at the rate of successes, is that generally the rate of successes is more than 80%. There is just one exception, which is DOT in Iran, where half of the lookups were failing. Because Iran was a mobile network and the others were VPSs, it may be that there is more censorship because it's more consumer facing. Okay, then another way to look at the data is to classify the endpoints where we observed failures by the resolver. I actually classified this into, let's say, buckets, Cloudflare and everyone else. And the reason is that I didn't want to give you a list of what was working and could be used immediately to bypass blocking, even if maybe it's obvious, but I didn't want to put this like in the table. So what does this tell us? It basically tells us that in the case of the Kazakhstan ISPs, really the most blocked thing was Cloudflare. In Iran, the percentage is very low. And indeed, what we did see in this case is that many services were really blocked. And then it's more of a mixed bags in China, but like still in the worst case, which is though, at least around 50% of the cases, they were represented by Cloudflare.
Simone,
Now,
can I jump in with a clarification question that came up in the chat? Are these percentages, do they represent the success or the failure rate?
In this,
on these slides.
in this table here,
yeah,
they are the no, this is failed endpoints, so the denominator is all the failures.
okay, thank you.
Yeah, okay. So let's now take a look at the failures and then what is the distribution of the failures. So the most common cause of failure in Kazakhstan is timeout after the TLS handshake. In Iran, instead, it's timeout during the TLS handshake. So what do I mean here with during after? We use Go, and the Go library returns at a certain point with either success or an error. If it returns with success and we see an error afterwards, it's timeout after. Otherwise, is timeout during. Then what we actually discovered when we managed to see some packet captures, which is not easy for us because OONI is really user space, is that timeout after actually means that you send the client hello, you get the server hello, and then you send other stuff that concludes the handshake. But what actually happens is that you later retransmit those bytes. So it probably means that the blocking kicks in slightly after the client hello somehow, but in time to receive something from the server. Whereas TLS handshake timeout looks like you send the client hello and nothing else happens after that. In China, it's different in the sense that it's much more common to see that connect times out directly. So what did how does this change when we use DOH? Well, it's similar in Kazakhstan. Again, the same most common cause of failure. It changes in Iran in the sense that before we had TLS handshake timeout as the most common. Now we have timeout after the handshake, and also it's actually spread out. So we have also connect timeouts, resets during the handshakes, and many other errors that together they are 20%. In China, still we have connect timeout, but it changes in the sense that before we had TLS and shake timeout, and now we have a reset. We think this probably means that since DOH is HTTPS, there was already some rules and infrastructure for filtering, and probably the filtering of DOH is very related to that, whereas DOT is a different protocol, and so it seems plausible that we see different things. So I'm approaching the end of the presentation. I want to conclude with 3 examples of what we have seen. This first example is an example in Kazakhstan. And this shows that in this case, the blocking depended on the SNI being used. So what's the SNI? SNI is the server name within the client allow. And so in this example, first column, we see that the same IPv6 address is always used, but the second column shows us that the SNI really is related to the result. So with cloudflaredns.com, we failed at 86 times, albeit in one case it was connect timeout. And then in the third row, we see that with mozilla.cloudflaredns.com, it actually worked every time. So this indicates that very likely the SNI is the culprit here. And this is now let's see the converse example. This is DOT in Iran. And here, basically, we see that 8844, it fails with an SNI, it fails without SNI, and that's very consistent. And then using the same SNI that was failing for 8844 with 8888, well, that's working every time. So this seems really to be a case where I would say the destination endpoint is the cause of failure. And well, we are not sure whether this is a DOS specific thing, or not. I was chasing a similar problem for China, but then I could not really reach a conclusion. And then finally, China. Well, this is a case where every time you connect, it's failing. And then the SNI is really superfluous here because it's actually you actually don't even have a chance to send out a client hello. So what are we going to do next? The first thing, we want to make DNSCheck available to all users rather than just the users of the experimental client, which means basically that every user that taps run all will run DNSCheck. So we will hopefully soon have much more data than the data that we have seen so far. We want to continue studying quick, not only in the DNS, but more in general. But yeah, it's a new protocol, and it seems reasonable that it's either, I would say, blocked differently, or it may work in cases in which the other protocol, like TCP, is not working and maybe fail in other cases. We want to experiment with the encrypted client allow in the sense that we have seen cases like this one here, where the SNI matters. So it might be interesting to see if ECH works and if we are able to query a service using ECH. And then the final thing is that we are hearing from some users that there are cases in which the fingerprint of the client hello could be a problem in a way. And so we want to improve our engine so that we are able to really parrot existing very popular clients like, I don't know, Google Chrome. And so there's a Go library that helps to do that. And we are planning on integrating it and, well, let's say making the measurement better by also trying this mechanism. Yeah, this is the end of the presentation, actually. So these are our contacts and where you can find us.
Okay, thank you very much for that. We have one question in the chat at the moment, which is from Alison Mankin. The question is, are you using TLS version 1.2 for the tests generally? You mentioned TLS 1.3 specifically on one data line. Okay, so we need to divide the measurements that we run basically into what I've told you about is a case where we configure
the client to request for all the versions. However, we also had the doubt whether it was maybe related to the version of TLS, what we were seeing. So we also on the side manually ran some measurements with TLS 1.3 and it didn't change the outcome.
Right, okay, thank you. Alison, I hope that answers your question. I was going to jump in with a quick question of my own, which is, am I correct in understanding that you've also been able to do some observations in India, which actually produced slightly different results?
Yes, it's not included here, but we did some measurements in India before. And so going on memory, it seems there was no blocking in India, if I recall correctly. Yeah, one of the persons that helped me do this is Grushabat, and he should be here. So maybe he remembers better than me. I'm actually a bit unprepared now on these measurements in India. I don't fully remember the result.
Apologies. Gershabad, if you...
Yeah, we tested for 3 ISPs in India, and none of them were blocking either DOT or DOH traffic.
And if I recall, one of the thoughts was that there's some greater regulation in India, which might have led to that, which I think is an interesting observation, you know, that related to these blocking activities. Is my recollection roughly correct?
So yeah, I think it sort of fits in the in India, the government is asking ISPs to block certain websites, but we haven't seen a history of them trying to block censorship circumvention mechanisms or specific protocols. So we haven't ever seen that, and sort of these results are consistent with that. Of course, the question was still worth investigating because ISPs do not comply uniformly with government orders. So we have some non-compliance issues, and some private interests may have led ISPs to block the protocols. That's why we wanted to investigate that question. But yeah, we found no blocking at the end of the day.
Okay, thank you for that. Any other questions for Simon? Yeah, we have one from Ulrich Visser. Go ahead, Ulrich, please.
Hello, sorry. Yes, I wanted to ask, because there was so much blocking of Cloudflare, could that have to do something with the IP addresses being formerly used as a research network and being like, you know, I think Cloudflare did a lot of work to make these IP addresses workable overall, and maybe they just didn't succeed everywhere?
Yeah, that's a great question. So also a colleague of mine suggested to look in this direction, and that's the only thing that I checked for quick, basically. And so quick for 11111 was working, which means that it was possible to route to the address, and so I excluded this hypothesis.
Okay. Next question is from Puneet. Puneet, please go ahead and ask a question.
Hi. Hi. So I notice I'm Puneet. I represent Google Public DNS. So I had a specific, simple question about the DOT blocking for Google Public DNS in Iran. It was surprising that 8844 didn't work, but 8888 worked. Do you have any thoughts on that?
Yeah, I think I was also surprised by this. I suppose so this is something we have observed multiple times. Censorship is not consistent, and it's not that I mean, I don't know. We did this DOT measurement, a similar one, also 6 months ago. And then 6 months ago, the situation was more or less similar, but we tested more networks, and every network had its own set of rules. So maybe you could use 8888 in one, and you could not use it into another network. And yeah,
could everybody please mute? We're getting a little background noise.
Yeah,
Thank you.
it's patchy. I was also surprised by this, but I actually suppose they do not always systematically do that. It may also depend maybe on the traffic, or yeah, it's unclear to me as well. Yeah.
Thanks.
Sure.
We have one comment and one more quick question. The comment is, it might be interesting to investigate Kashmir separately because of additional regulations and defense mechanism in place. Sorry, that was a comment from Sudesh.
Yes.
And we have one question from Wansundra Raman, who says, did you use only one VPS in Kazakhstan and China? You mentioned seeing a well-known block page IP address in Iran, but do you know whether the blocking in Kazakhstan is specific to certain ASs or countrywide?
Okay, so in Kazakhstan, we used the two networks. One of these was a VPN and the other was a VPS. We didn't see much stuff on the VPN, so it was probably not a good idea to continue testing with it. And that was the only VPS through which we were given access. I know that the structure of the, anecdotally, let's say, the structure of blocking in Kazakhstan is slightly centralized, but I also looked at the, so there is a Kazakh Telecom ISP, which is the one that, according to papers, should be a place where they do blocking. It does not look like to be an upstream of the ISP in which we were in Kazakhstan. So they were exiting towards another route, which probably means we didn't pass through, well, if my guesswork about how we were leaving the ISP is correct, we were not passing through the main, well, the Kazakh Telecom, which is told to be one of the choke points, but still we could see censorship. And what was the question regarding Iran?
The question was about Kazakhstan specifically.
Okay.
Yeah.
Okay.
So,
okay.
So it said you mentioned seeing a well-known block page IP address in Iran.
Yeah. Okay.
So Ram, I hope that answers your question. With that, I think we're done with the questions for this part of the session. Thank you very much indeed, Simone, for your talk. Very interesting data there, and I look forward to more future research on this topic. So we will now move on to the last talk in this session. This talk is called No Port 53 Who Dis? A Year of DNS over HTTPS over Tor, and it's presented by Alec Muffet. Alec, please go ahead and share your screen.
See if this is working. Can everyone see this?
Yes, we can see that.
Awesome. Let's see if I can also play this. That makes it go better. Hello, everyone, and I'm delighted to be speaking to you today. Thank you to the chairs for giving me the opportunity to present this. I want to sort of start by working backwards. It's lockdown, COVID is changing all our lives, and my partner and I have been at home using DNS over HTTPS over Tor exclusively for an entire year. And it's worked fine. It's worked marvelously. It works so well, actually, that I set it up about this time last year, so it's February to February. And then I promptly forgot that I'd set it up until July because of lockdown happening and sort of all the chaos of trying to work out what we were going to be doing and where we were going to be living and so on and so forth. So it's a system which is meant to provide extra privacy and security for your DNS queries. Some people have done it. If you look around in the on the web, you look at people who've tried it before. They say latency is going to be terrible. It's a disastrous experience. All of that is wrong. I can say this quite categorically. It turns out that at home as a client, it's not actually too bad to live with a median DNS latency of 250 to 500 milliseconds. And this is possibly heretical for those people who research and try to drive down latency. But at the client end of things, for certain populations, this is okay. I can say for sure that where's my click on? Yeah, the latency that we've got measured, I've now in the last 7 months, ever since I remembered I'd switch this on, I've logged 2.4 million requests through a little stub DNS resolver I've set up. Doing DNS over HTTPS over Tor, the median latency for request is 260 milliseconds, and that goes up to 460 if you switch off caching. Oops, pardon me. Some people live with these kind of latencies day in and day out, and I'm grateful to the people who reviewed my draft pitch for this presentation for raising the question. There is no standard metric which is usable to get an image, get a picture of someone's experience. And so I tried to invent something. I wrote some shell scripts that would make 5 attempts to look up 100 random IP address backwards in DNS using dig-X. Very basic, very sort of brute force and stupid. But then I circulated that amongst friends, all of whom are geeks and nerds. And I was astonished that doing DNS over HTTPS over Tor this way, measuring it against all of the competition, so to speak, it was in the 70th percentile. It wasn't even at the far end. I consider this an acceptable experience. And if I go and look at the competing experiences, some people are just trading off latency against the likes of privacy. For instance, Pi-hole, some of them were faster and some of them were slower, but people were using Pi-hole in order to assure a little extra privacy, not get adverts, and improve their user experience. Similarly, some of the people with longer typical latencies were in places like Ireland or Russia or Greece and other places which are less well served by backbone. So my takeaway from this little experiment, and all of the code is available, everybody can get at this. My takeaway from this experiment is that if we're arguing about 5 milliseconds versus 50 versus 500, we're actually being kind of presumptuous about what people want to achieve and what they would like to get from their DNS queries. Latency is not everything. It's only a portion, a fraction of the user experience and the value proposition. It's one that is very easy to measure, especially for nerds like us, which is probably why we are so hung up on it. But it isn't the big picture, or it isn't all of the picture. If you accept this as a perspective, you might as well treat it as a sort of budget, and you can take this latency budget, which you're allowed to inflate a little bit, and get better privacy value. So let's look at doing DNS over HTTPS over Tor. What is the rationale? Well, if we build a threat model and say that the ISP we assume is going to either block a port wholesale or some tuple of IP address and port, for instance, trying to block port 53, which isn't destined for our sanctioned DNS resolver. If that's the model of blocking, but you probably aren't going to be able to block port 443 HTTPS glibly, you can't just wildcard block it because it's what people do. If you take those as assumptions, if you assume that Tor works as advertised, and that HTTPS adequately assures identity as certificates, then this was built to try and protect against the threat model of a privacy invasive actor who would surveil my networks, block or tamper with my queries, block or tamper with my responses, pretend to be my chosen proxies or resolvers, and then would associate my query or response with my identity. That's point 7 in this threat model. The other two things which I've added to this have been alluded to in previous talks. One is what I call sort of synthetic collusion, where the National Security Agency or some other actor parks a big observation deck on top of the resolver and the proxy and can sort of do time-based correlation of what comes in and what goes out, and thereby synthesize some sort of collusion, or alternately just actively FISA or subpoena logs or something like that in order to get information which they can glue together and rebuild queries backwards and work out what people were doing even though it was encrypted. DO53 risks everything. It is insecure. DNS over TLS, you can block it. You can do second-party surveillance where the resolver knows who you are, or third-party surveillance or collusion, which is the NSA knowing who you are, for the sake of example. Other security agencies are available. DOH, also second-party, third-party surveillance or collusion. The oblivious protocols that we've seen recently, including ODOH, which was spoken of earlier, do a much better job. They tend to reduce the risks down to third-party surveillance or collusion, but they require informed users, as has been already touched on. It's worrying when the proxy and resolver are co-located very closely, or indeed logically or legally co-located. Then it's just a simple data grab. Whereas doing DNS over HTTPS over Tor risks arguably none of these, especially so long as Tor is working as advertised. So as I say with ODNS and ODOH, the designers of these protocols are primarily focused on minimizing latency impact. We see lots of lovely curves showing that, and I think this is important research. I think it's great to see some development in this space, but it worries me because they're choosing single layer proxies that are open to selective blocking, like Russia did to AWS, like Iran did to Signal, versus things that the Tor project are actively combating. You also see as I said a little bit earlier, both sides surveillance where you just look at the resolver and the proxy and you use time-based correlation in order to synthesize collusion to glue the data back together again. So I'm a little concerned about them. Whereas on the other hand, if you want strong DNS privacy today, you can deploy this. It doesn't require any invention. It's free, it exists, it requires no new toolings. I invented nothing. I can take no credit for this other than pulling together a config file and the presentations in front of you. You're in control, you can roll your own. It's an operational practice, it's operational security rather than a protocol. Downside of this, you get to go to less interesting conferences because you're not doing pure research. The performance is on par with Pi-hole. There are already privacy-centric communities who will make value trade-offs, latency versus privacy, on the privacy end of the scale. So I think there's a community who would like to adopt this. The architecture, because there always has to be an architecture slide. I took a copy of DNS Crypt Proxy, configured it as a stub resolver, said do everything over Tor, minimize the fingerprintable metadata like session tickets and ciphers are all standardized, at least if you're using my config. And you put it into a pool of load balanced resolvers. The interesting news, which is why this slide deck is slightly updated from the version currently available from the website, is I took the restrictions off yesterday. Previously, I was only measuring 9 DOH servers and just said, how many DOH servers are there in the world which DNS Crypt Proxy knows about and which it would use? Answer, 48 servers from about 28 providers. So there is no reason for you to centralize all of your data. The big myth about DOH promoting people giving all of their data to Cloudflare or giving it all to Google. You've actually got 28 different services. You could smear your digital fingerprint across whichever ones of these would be most effective, most responsive at any given time. But that's the only reason that that your data would be subdivided. You've essentially opened up a free market in competition to whoever can respond to your query fast enough. So this leaves me with a small series of questions, which is, if we can address the entire threat model, this threat model, within a reasonable latency budget, why should we restrict ourselves to only addressing a mere subset? Some folk I've argued with regarding this is that DNS privacy is something we should fix centrally, and my take is no, because DNS, all the arguments I get into say DNS is a distributed protocol. Distributed protocols require active clients and active participation of clients. So I'm happy with doing this and doing a solution based around DNS over HTTPS over Tor, at least for certain purposes. We need to solve this for everyone. There was a question a little bit earlier similar to this. Who is this for? Well, I don't think it needs to be a solution for everybody. It could be. Maybe if we make Tor more popular, that's one way of approaching that. But it's a matter of, are you building something for a wide population, or are you building something to minimize latency? I'm not doing the latter. I've given up on latency because I find it absolutely livable. If DNS goes dark, then the authorities will be forced to regulate DNS even more. This is the original nickname for this project in my head was DNS Dark. But if we look at the capabilities of the democratic states of today, they will be the capabilities of totalitarian despots tomorrow. And I think we should be optimizing to protect against the latter. This is my threat model, and you are willing, I'm happy for you to argue about it, but if you do want to argue with my threat model and why I've built it this way, I'd like to know why you are not defending against certain aspects of it. And if my stats are dreadful or inadequate, please go and research, replicate this. I'm very happy to see other people doing this. I give this away with no pride, because this is just literally, I built this thing, hacked it up, and have lived with it for a year. That's not exactly great research. It's just useful to share. So if you have any ideas on how this can be improved, please let me know. I'm always interested to hear. I would like to know whether people find it an exciting and enticing idea. And if you remember only one slide, it's this. I ask people to please stop thinking of latency as a cost. Think of it instead as a budget to offer value to the people who use DNS and who want privacy. And that's the URL for the project. Thank you very much.
Alex, thank you so much for that talk, for your personal commitment to the research as well. We very much appreciate it. And for bringing the work to this workshop. We do have a few questions lined up in the chat. DKG, you have a typed one and a +Q. Are they the same question?
They're different questions.
Do you want to just go ahead and ask?
I feel like I'm jumping ahead of Chris, who got a +Q in. Why don't, Chris, you want to go first?
Oh, no, go ahead, DKG, it's fine.
Okay, thanks. So Alec, thanks for doing this. This is a great report and a great challenge in terms of encouraging people to think about these problems differently. I had a couple questions just about the way it played out technically. So my first question, which was written down, has to do with whether or not, if you can characterize the typical workflow for people who use your network that this was deployed on. For example, is everyone using ad blockers? The latency budget multiplies on the web when ad blockers are not in use, as I understand it. So I'm wondering if that had any effect on the way that it worked.
That's a really interesting question. And if I understand it, you're essentially asking, because this is domestic environment. It's me and my partner and anyone who happens to be visiting the house.
Yeah.
They connect to DHCP. DHCP says this is the IP address of your resolver, and that happens to be a Raspberry Pi, which is running this stack.
Got it.
And that's all there is to it. I exhort people to read my report. Apart from anything else, hopefully it's more fun than your average white paper. And all of the stuff is in there, I promise you.
Yeah, but so I guess what I was asking was, the people, when you're saying this is livable, you're saying it's livable for you and your partner and whoever else visited, which given lockdown is probably not that many people.
Correct. So, indeed, and this is one of these questions which comes up a little bit like Tor in its own sense. One does not typically run a Tor daemon for an entire office and have everybody talk to that over socks.
Right.
What one does is instead run one locally. I'm wondering where this fits myself. Like, would you roll this out for a coffee shop, or would you have this run on everybody's laptop independently? I think there's some scope for research here. But I've hammered it. I've hammered it pretty considerably with those shell scripts, and the experience of all the people who are using it suggests that many thousands of requests a minute, not a problem. If you're pushing it above that, you're probably in a different world anyway.
Right. So my other question had to do with the way that you configured the link between your Raspberry Pi device and the various DOH servers. And it had to do with questions about persistent connections. because that's the one place where the linkage seems to be retained across Tor. If you hold open persistent connections and pump multiple queries into them, then you build a sort of correlational profile within that bundle of persistence. How did you configure those trade-offs?
The configs are available for your review, but the short version is 30-second keep alive and the P2 load balancing strategy that's built into DNSCrypt proxy, which is where it randomly picks one of the 2 fastest connections to fire the request down. Plus, it also randomly connects to one of the other machines in the remaining pool in order to refresh the permanently refresh who is the top 2 fastest connections. So your query will wind up going to at least 2 machines, which could sound like you're actually inflating your digital footprint, so to speak. But it's also very standardized and very stripped down. So most that Cloudflare or Google or PowerDNS are getting is a small batch of queries before the load balancer moves on and picks somebody else.
Yep. Thank you.
And the other goal here is that if other people use this standardized config, they wouldn't be able, PowerDNS or whoever, wouldn't be able to tell one batch from another batch.
Thanks.
Thank you for that question. Next, we'll go to Chris Wood. Go ahead, Chris.
Yeah, thanks, Alec, for presenting this. I wanted to drill in on the threat model. Especially when comparing this against something like ODO or Oblivious DNS or Anonymous DNSCrypt. You had mentioned, or I think the slide said specifically, that you're assuming sort of this NSA-inspired type, actor that could potentially be seeing all things at all times and doing endless compute to figure out or to try to track down what a particular user is doing. But to me, that seems like this threat model does not really scale. Like if you would imagine like every client in the world using a version of anonymous DNS, be it over Tor, be it ODO or whatever, do we really think that there is enough sort of compute, storage, everything available for an adversary to be effective in trying to single out an individual client? I'm highly skeptical of that.
And I'm highly skeptical too. I entirely agree with you. You are correct. What I am saying, on the other hand, is that the oblivious proxies are an extremely target-rich environment and are essentially a watering hole for a watering hole attack, which is you watch it, you log everything, you throw it all into a big Oracle or whatever database, and then you mine it when you need to.
Understood.
Also, there's also the other thing is that I still also think they're a small target. Tor is actively developed in order to combat things happening like Belarusian lockdowns and Russian attempts to block something. Plus, it's got an entire ecosystem of bridges and other proxy software to bypass this. Whereas DNS is whatever the RFC says, plus whoever has managed to implement it.
Yeah,
I feel it's a richer ecology of privacy and privacy bypass and blocking bypass to work with than is going to be hard codable into DNS.
Yeah, I mean, I don't disagree. I guess this just boils down to like what the threat model is and what we think is sort of feasible and what risk we're willing to accept. So
yeah, I very much I used to work at Facebook, and let's just say that the Snowden revelations hit me fairly hard in terms of what people are willing to invest in order to try and get at back-end infrastructure and to build added value into X keyscore, cross keyscore queries.
You were not alone.
Yeah, that.
Thanks, Alec.
Okay, thank you. We have one more question on the talk from Paul Severson. My understanding is that Tor browser does not currently support DOH. This raises a learning curve stroke usability issue. How off-the-shelf usable, assuming you know how to point at a chosen resolver, is the DOH at the moment, and are you working on that?
Hello, Paul. This is the man who invented Tor, basically. And yeah, I am not working on this because it's a home setup thing. I threw up a Raspberry Pi a year ago and hacked something up in the space of an evening and then forgot about it for 4 months. So it's hardly like I'm investing in it or there's going to be a startup anytime soon. I greatly encourage people to experiment in this space of their own accord. That said, because DNS discovery is something which is so heavily automated, and since we have this lovely DHCP packet, which literally tells you where to go to find your local DO53 resolver, the only thing which I've done in extension to that is to block port 53 at my firewall and port 853 as well. Nothing gets in or out other than going through DOH. This includes my slightly upset Chromecast, but it's fine. It continues to work, even though every 22nd it plaintively tries to call home on 8.8.8.8. But apart from that, yeah, it's easy if you set one of these things up. You could easily turn this into an appliance. I would love to, and have sort of vaguely reached out to the Pi-hole people to ask if they'd like to have this as a tick box item on some config. I think that would be a great place to have it. And we can then start to build a profile of what it's like to add DOH to some anti-advertising filters and other kinds of PHP and Python slowness that reduces the speed and increases the latency of your DNS queries anyway.
Okay, that's great. Paul, I hope that answers your question. And I've now learned the right way to say it, which is DOH for the new acronym.
I don't know.
Thank you. let's declare that. Okay. So I think that's all the specific questions on this talk. I'm sure there'll be some more discussion on the general topic. Thank you, Alec, very much for presenting that. At this point, we have a few minutes left for the open discussion. I'm going to return firstly to the outstanding questions from the Oblivious DOH talk earlier. And what I'd like to do is open the mic to Chris Wood, who I believe wanted to respond on the general point of the use of multiple proxies in a round robin manner. Chris, are you happy to talk to that now?
Sure. I pointed a link to a draft that Martin Thompson, Yarko, and a couple others wrote, where they effectively try to discuss the various trade-offs involved in choosing, which resolver to send your query to amongst the various set, and like what sort of leakages incur. And my point was that it's very much context dependent and application dependent as to whether or not you're actually leaking information if you spread your queries to multiple resolvers. So it's not clear to me that any one scheduling mechanism will be best. And I don't know if we have an answer to, that particular question. It seems to be that picking a particular resolver and just pinning it indefinitely for a particular user is best because it minimizes the chance of potentially spreading your queries elsewhere. But that is my intuition. I have no formal backing for that.
Okay, thank you. And I'm gonna just pick up one question that again was on the ODH talk, which was taking into account forward secrecy and the way ODO established the connection to a resolver via the proxy. Do you think that a proxy logging IP data is a huge threat to privacy, since upon leakage of the private key of the resolver, the proxy would also be able to infer which domain the IP tried to connect to? And so I guess that's for Sudheesh or Chris, if you can speak to that.
I think that is definitely a risk, which is why in a production system you would want to rotate keys quite frequently, like with some TTL value. But yes, that is definitely a risk for logging proxies. So if there is a logging proxy, similar to how maybe some like anonymous DNS crypt, there are some logging proxies. It's the client's choice at the end of the day if they would like to use it or not.
Okay, and sorry, I should have said that question was from Medoti Mikov. I hope that answered your question, Medoti.
Yep, thanks.
Okay, great. So we do have a few minutes left for other questions on general topics. I see one in the queue, but please jump in now. if you have any others on any themes that have been raised during the session. I'll turn to Paul Hoffman now for his question, please.
Thank you, Sarah. So this question actually applied to almost every one of the speakers so far. So I don't know who would answer it, but it seems that all of these things that we are proposing require the user to understand privacy, require the user to be able to balance, for example, in Alex's case, privacy versus latency and such like that. Doesn't this go against everything we know about typical users? Or are we really designing these additional things beyond what we have now really only for intelligent, privacy conscious people? I mean, those are hugely different audiences. Who are we designing these for?
I could have a go at that.
Please go ahead.
That's a great question, Paul. And reflexively, I would turn it around, which is, are we designing our protocols for speed demons? Or instead for people who want to solve a problem? And I lean towards the latter. People make choices. People install applications that allow them to do something. Even if it's a bit slow, it enhances their life by allowing them to achieve some goal. And this kind of realization that even a crap app, which at least gets someone a little bit more forward in terms of what they want to achieve, makes someone's life better. So there are folk who use Tor browser all the time because they want privacy. Are they willing to accept the performance trade-off? Yes, they are. I don't see that that's discriminatory. I don't see that it's elitist. I see that it's offering value to these people to solve what they perceive to be an important issue for them. Perhaps, therefore, the issue is whether we continue to think about this in terms of protocols and latencies inside protocols and all the technical stuff that we've been doing for the past 40 years, or whether we see it as applications that try to fix people's problems and give them a value proposition.
So I could also take a little shot at it and try pushing back a little bit on you, Paul. It might feel like this is designed for the elite or someone who knows exactly what they're doing, but that's kind of how encrypted transport protocol, like encrypted protocols like HTTPS actually came into existence. So it was at one point used by very few, but then there is this push from the entire community to kind of get everyone onto HTTPS, and most people don't even kind of like notice that anymore from the push that we've had. And I kind of feel that the push for DNS is going to be kind of like that. As you get operating system providers to automatically support and check if an ISP that the user is connected to supports DOH or ODOH or something like that, and then basically ask the user some interesting questions, which I think we might cover some of these in the next section where we speak about usability of DNS, and there are some interesting talks about user expectations around this. So maybe I wouldn't treat that the users are dumb. The users clearly do know what they're talking about or what they want to do.
Sandesh, thank you very much for that perfect segue into our next section. Thank you, Paul, for the question. I'm afraid we're out of time for this session, but what I was going to say is that I think this was a great question from Paul and a really important topic. And what I would encourage folks to do is join in the breakout session at the end of today. And if they're able to dig into this a bit more and write some notes and brainstorm some ideas for what we can do to understand this question better in future. With that, I will thank everyone very much. Thank the speakers in the session. Thank everybody for their questions. It's been an excellent discussion, and we can continue this later on. We will return in half an hour. Half an hour will be the start of section 2. So please enjoy your break, chat in Gathertown if you would like, and we will see you in half an hour's time for session 2. Thanks very much.